kind of managed to you all kind of managed to play with the absinthe sim to have an idea on what is the UV, the measurements that you can get depending on the different array configurations that you use. You also have an idea what is the effect of observing more or less hours, what is the effect of the source coordinates in your projected baselines as well. But yeah, okay, the question arises on the rightmost windows that you have, the dirty beam and the dirty image. So I was explaining you all the time. I said that the dirty beam is the response of the telescope to a point source. Okay? Ideally, if we, so remember that
of the point source located on the Earth, right?
Of the points.
The beam is the response of the telescope of a point source located on the Earth.
Yeah, in the center, yeah.
The center.
Yes. A point source of, let's say, flux 1, okay, located in the, So you just have a point source in the center, and how would the array image, what would be the final image of that point source? So if we were able, again, okay, sorry. We have measurements, visibilities in the so in the UV plane we measure visibilities, and if we so this is the Fourier transform of our image plane. Okay. If we had all the possible visibilities measured, so then we have a continuous function. We will be able to make an image which is exactly a point source. Okay, but we have an array, which are a limited number of antennas that are moving as the Earth rotates. So we don't have information of all the visibilities, right? We just have some visibilities, and with that, we cannot obtain a perfect point source. We are sampling our visibility space. So the dirty beam, okay, sorry, I was choosing the wrong presentation. Okay, we are already moving to the imaging part. So we are working in the Fourier transform space in order to retrieve what was the original imaging plane. Okay, but we are sampling that space. We just have information on the baselines that we have, no much more than that. So discrete points in your UV plane, you can see there, just discrete points. So we are sampling the visibility, the UV plane. The dirty beam, sorry, the dirty beam is the image of that sampling. Is that, are you getting it? Kind of? So if we were able to measure all the visibilities in the window, in the right top window, you will get a perfect point source. But this is not the case.
For that, we would need like an infinite
Yes.
number of antennas.
Yeah. If in the perfect ideal scenario that you have information of all the visibilities, then you get the point source. The goal with the interferometer and with the Earth rotating is to try to sample this UV plane as good as possible, so we can image a point source as a real point source. But we will be always limited by the configuration of our array. So we will have a minimum baseline and a maximum baseline. So we will not be able to image a point source as a point source because we will have at least expanded that point source to look like the maximum resolution that we can achieve. Okay? So that's the result that we have in the dirty beam. If you guys play with different arrays and observe for long hours and map and sample the UV plane as good as possible, you will be able to have a dirty beam that looks like a point source. And the more it looks like a point source, the better your observations are. Okay? I hope that it's clear. So what we are having in the right lower panel, it's a dirty image. Okay? Ideally, again, if we were able to have all the information from all the visibilities, our image will be exactly as our source, right? But it's not the case because we only have information in certain for certain baselines. So the same way that we cannot recover a point source as a point source image, our source model, we cannot image perfectly as if it was. We have that limitation. So here, so the dirty image is our image multiplied by the sampling. Okay? And we will try to get this image here, getting rid of our sampling noise, our sampling effects. And this is what we call like the convolution. We will make the step backwards to get this image here. Okay? Okay, so I think well, there are perhaps there are different ways of doing this, the convolution. There are several algorithms to try to get the best source model that that fits this dirty image. So there is a clean algorithm and also the MEM algorithm and multi-scale algorithm. So I will try to just briefly explain you how they work. For that, I also made use of some slides that I point you here from the NREO school. So I hope that you guys understood, all of you, what is the dirty image and what is a dirty beam. Yes? No? Yes?
The dirty beam is always the same image or depends on the real image? Because I don't...
No, so the dirty beam is independent on the source that you are observing. It depends on the sampling or on your array.
But I thought that, but I changed the real image and the dirty beam changes. Even if I don't change the array, here's the real image and here's the dirty beam. I will change the model.
It shouldn't, for exactly the same.
Maybe it's a book.
But something else is changing when you are loading again, right?
Yeah.
Did I see it right? That is changing also some.
Look again. And everything.
Is changing something else, right?
The axis altogether. So it's an effect of change also the axis. I mean,
Because it changes the now.
Yeah, it changes something else. Yeah, you are right. Yeah. Okay, so yeah, so you get it, right? The dirty image is the true image convolved with the dirty beam. And what we want is to undo that step to get what is the real image. Okay, this is an example. Perhaps you cannot see it very well, but it is I think it's an ALMA observation as well, an ALMA configuration for a short time, perhaps. Yeah, so that would be the dirty beam for such a coverage of the UV plane. Ideally, if we had all of it covered, like everything in black, all of it black, here you will have a perfect point source. Okay? If you are not covering, you have been playing with that. If you are not allowing a lot of time for the Earth to rotate, then you are losing spatial information. You are just sensitive to one direction, perhaps. So you really want to have this as better coverage as possible. Yeah. So that could be the convolution of the dirty beam with the true image. This is the dirty image that we get. And we would like to recover this. Tell me.
That's the part I don't get, like the order of how we do things. Like, how
This one we don't know. Okay? This is the real image.
That's what we want.
That's what we want. But that we don't know. We are just getting this.
How do we get that if we don't know that? Which
We don't know that. This isn't, there is a source in the sky that is however it is,
yes.
right? And we are observing this.
But how do we observe this? How do we observe the dirty image if the dirty image is the convolution between the dirty beam and the image?
Yeah. Well, in this case, it's well, we have created this model to put it here to obtain this dirty image. In a normal observation, this is an unknown. And you are doing your best to find which model is this. Okay? This is an unknown. This is what you are trying to get.
So how do we get the dirty image if we don't have that? If the dirty image
You have a source in the sky that has a certain shape with certain brightness and certain distribution and short scale, large scales, everything, all the information. Okay? You have your array pointing at the sky, measuring voltages all the time. And then you get a dirty image. This is what you get.
That's what you get when you do the sampling.
Yeah. So the sampling of the array is this, but you are observing this.
And you take on board that dirty image and obtain the
Yes. Are you okay? Okay. So because of the sampling, there is a lot of information from your source that you are missing, right? You are only observing this. So there are infinite numbers of models of real images that could give you as an output this dirty image. Okay? You can, for instance, to this image, you can add up large-scale structure that will be lost by your sampling. You are insensitive to extreme large scales, right? So all the sources, all the possible images that have this extra large scale will result in exactly the same dirty image. We don't have that information, okay? So we will just try to get this as good as possible with that taking into account that uncertainty. Okay. Okay. We will not get our hands in CASA yet. CASA is the software that is used to do this process for ALMA data and for other telescopes. We will still be working with AbSynSim because it has the option to do the convolution. Okay. Okay, so this is, perhaps you can all go to reduce data and see what comes out of it. Okay. If you all go to the reduce data button, you will get a new window in which you have your, okay, one side is residuals and the other is cleaning. Okay, you are already playing with it. Excellent. Good. So what is this? Yeah, sorry. Okay, you because you are doing the okay? Okay. Yes, you are. Look at your dirty beam. So you don't have almost enough information to try to just get anything about it. Or perhaps you can close it and open again. Would be an option. Okay. So what the clean algorithm does, it's basically, I do try to decompose this dirty image into a sum of many point sources. Okay? So what the clean algorithm does is try to create a model which is the addition of just point sources all the time. So the way it works is that it basically goes to the dirty map and finds the maximum. Okay, and then it says, I will assume this is maximum is a point source. Okay, so then I kind of get this component, I subtract it from my image, and then I start again. I look which one is the brightest, the next one. I feed another point source. I take it out. So all the point sources that I'm fitting, I'm putting them aside into my clean image. This is why it's called clean. They are the point sources that I'm subtracting. They are called clean components.
So many point source programs here.
This is what you call, well, here it's kind of a number of iterations. Okay, this is because this is not the brute force, it has 2 cycles, but the number of iterations is basically how many clean components are you going to subtract. You have 2 ways of stopping this algorithm. In this case, you can choose a maximum number of clean components I want to in my image, or which is the maximum flux, which is the minimum flux I will stop. Okay, I will say at one millijansky, I don't care. It's just noise. I don't believe those clean components are real. Are just okay. They can be point sources, but they are noise. So the idea is that you just get bright enough clean components in your image. So let's say you have like a imagine that you just have a point source in the sky, and then you have your dirty images will be exactly the dirty beam. With one clean component, you are done. Because the algorithm goes into the image, it finds the maximum, it fits a point source, it subtracts it, and then there's nothing left. So you are finished, you are done. So in the case of a point source, you are easily done with, in the ideal case, with one single clean component. But the problem comes when you don't have point sources, when you have extended structures. So then in order to represent an extended structure as the addition of many, many clean components becomes problematic, because then you keep subtracting point sources and you never get it down. So you end up with some residuals. Okay, so your stopping point, you say, okay, I'm happy with that. The algorithm, what it's doing is, okay, I take my clean components and I add it to the residuals, and that is going to be. This is the way you stop. You could keep going all the time, so at some point you have to stop. So perhaps you can try to clean some images to have an idea how is it going, how does it work.
What's this? The true source convolve. That's when we do the convolving of the dirty image. Or what's this?
True source convolve with the dirty beam.
Because I
Okay,
think
so this is the clean, and these are the residuals.
Oh, that, right, yes.
And what you were showing me, I think it's adding these two
These
things, right?
I think I just click there and show
Yes.
this. Because I have one question.
And then you can go back, yeah, and show FFT. Okay. Okay. I was not playing well enough with this. You had one question?
What happened when I change the phase gain and the amplitude gain? What does it give to me?
Yeah, but this is for adding calibration errors, so we will look into that.
Okay.
So this is when the system is not behaving well and you have some antennas that are measuring something wrong. You also have an effect in your image, and we will talk about that later.
And I can change the calibration error in every antenna.
Yes, I think here you can choose. You can choose if, for instance, the antenna, whatever, has a bad response, or it's like.
And I can make as much iterations as I want.
Yeah, at some point, the thing is that you will be just cleaning very weak level.
At the end,
It will just adding. Yes, you are cleaning the noise. So you can keep adding as much iterations as you want, but
you want to stop it.
you want to stop at some point.
Okay, so
That's why you have to choose. You can choose in two ways, in the number of iterations, which is the number of clean components that I want, and in the threshold. If you say, okay, until up to this threshold, when it starts like adding at clean components which have very low flags, it's basically that you are just cleaning the noise. You are not interested in noise.
So when I know, because this threshold is Jansky over B,
Per beam.
because if I want to clean this thing, how I know how much threshold I should?
Is it not telling you? Is it not telling you? you can see what is the value of the flux in those points.
And I can
And
put
then,
that
Yeah,
threshold.
yeah, you can put this threshold to be
Okay, so
to be
I
that.
could.
You can give, yeah,
10 Jansky.
Tenjansky, okay, and then you can give like 1,000 iterations
And it should start
when you reach the level.
okay.
Yeah. So I think